thank you very much. I would like to thank the organizers for inviting me. And I would also like to apologize because the material I'm going to talk about is already several years old. And some of you have already heard me talking about this maybe more than one time. Now, today I will start to touch the second part. I mean, the second half of the title of this workshop, namely foliations. So let me start with introduction to foliations. So to do that, let me start with something even simpler, namely differential equations. So let's consider two ordinary differential equations. The first one is dy over dx equals a times y. And here it's very nice because I mean everything is like using algebraic functions, actually polynomials. But the random thing happens is there is no non-trivial algebraic solutions. If the number a is not equal to 0, right? The second one, we change this slightly a bit. X times dy over dx equals a times y. Then we see that you can have a solution y equals some constant times x to a. So this will be algebraic if and only if this a is a rational number. Okay, now what we do is we change the formulation slightly different. So a different formulation. Namely, we consider a D, which is rank 1 subshift generated by the element d over dx plus ay d over dy as a rank 1 subshift of the tangent shift of a2. Okay. Then you ask what are the functions on a2 which is killed by elements inside this sheaf. So I will just write df equals 0. Well, it turns out that because of this, here we only get basically constant functions. So you don't get anything interesting here. The second case is you take this d to be generated by the derivation, which is x d over dx plus ay d over dy. This is also rank 1 subshift of the tangent shift of a2. Then you do the same thing. You consider algebraic functions, which is killed by, actually, not quite. Actually, here you also consider localization is not a global function, so maybe you just with functions defined on some open set. Well, this is strictly bigger than C. So we get some interesting functions inside there. Namely, functions look like this. I mean, if if a is a rational number. Say, I mean say if a is an integer, then this y divided by x to the a would be a function inside there. Okay, so that's ordinary differential equations. So from the second formulation of the equations, we get a notion called foliations. We define, say, let x over some field k be a quasi-projective. Maybe also say normal to make things easier, normal variety. So then a foliation x is a, usually we take saturated subsheaf called D, which is inside the, the tangent sheaf of x, such that D is closed under Lie bracket. Namely, if you take two local sections of D, you do the Lie bracket, which is again give you a derivation. You want that to be again inside D. So that's a definition of foliation. Here I don't put any restriction on the characteristic of K. So it can be in positive characteristic. So then, example. Oh, well, it really depends on how you define the foliation. In this talk, I just defined in this way. Then I will say, okay, I put an extra condition saying that the D is P closed when I want that. So examples.
So what is your assumption on K?
K is here. Well, currently I just say some field.
Any field.
Yeah, any field. Now, so if rank of D is 1, then it's automatically a foliation. I mean, if some subsheaf inside T rank 1, then it's in foliation. And well, the second example will be example that we are very interested in. So if I have a, say, fibration of x, maybe even just a rational fibration over some b, then we can define D to be the relative tangent sheaf Well, here, if this is not a morphism, just if it's only defined on an open set, then you can define this D on that open set, then you take the saturation of that sheaf, and you get a D inside the whole tangent sheaf. So if D comes from a fibration, then it's automatically foliation. Then D is a foliation. One very interesting question is, if you start with a foliation, you want to ask whether.
If D is what? Then always or what? If it's a fibration.
Yeah, if any fibration, then you get a foliation, which is just given by the vertical tangent directions. Right, and sometimes it's very natural to get some kind of a subsheaf of the tangent sheaf, but to get a actual fibration, it's usually very difficult. I mean, if you just start with a subsheaf, you want that to be coming from some fibration, and it's a very difficult thing to get. Okay, and let me see. Right now, for this this example says from foliations you get foliations. Now what about the other way around? We define we get the following definition. A foliation B is algebraically integrable if this D is given basically given by for some vibration. Okay, so that's what it means for the foliation to be algebraic integrable. Because we do algebraic geometry, we want everything to be algebraic. But I just remarked that if you do differential geometry and then basically everything is integrable. So in analytic category, we have the Frobenius theorem. This implies if you take the D is analytically integrable.
No.
Yes. Well, because here I'm just defining this on some open set. It should, right. Okay. And we also know that most of the foliations we get, you just write an arbitrary one. Usually it's not algebraically integrable.
So in your definition of algebraically integrable, B is a curve or it's a disk? Or it's something,
it's some,
a jam,
just some variety.
Some variety, so some variety.
Yes. Not
you want something local or something global?
Why would say something global?
Global.
Yes. So, and well, let's look at the examples I have. So, when the first one D equals is inside A2 is not algebraically integrable. Well, before doing that, maybe I should also mention that to get if you start with the foliation, you know that it comes from some vibration. Now, how do you get this vibration? The way you do it is try to get the functions which comes from B. Those are basically the functions on X, such that they are killed by this foliation. So that's the, so then, this gives you the relation between, the differential equation formulation and the algebraic integrability here. Now, we know that this one is not because there is no algebraic function which is killed by this foliation. The second one, this is algebraically integrable if and only if this A equals, is inside is a rational number. So in that case, if we say A equals A equals something like n over m, then D applied to y, m and x to the n, this would be 0. And you can define map from A2 to A1, map x, y to x to the y to the m divided by x to the n. Okay. That's the b you get here in the rational map. Okay, so this is what, right? I should here. When we talk about algebraic integrability, I should say that it's only interesting, basically, characteristic of k that equals 0. Oh, well, you can also talk about it like this definition in characteristic P. And it's well, you will see like it's not that. I mean, the relation is not that like kind of close, because foliation basically gives you like a first order of some vibration in characteristic P. Boy, did I? Okay, this should be 1.3, 1.4 here. So now if we characteristic P is 0, then we will think about the foliations. These are somehow the same as purely inseparable morphisms. Okay, now we know that if characteristic of k equals is positive, then any derivation x will give you you can raise this to the p power. Well, usually, I mean, in characteristic 0, this will give you degree like a differential operator of order p. But in characteristic p, this is again a order 1 operator. It's again inside there. So then we can define a foliation is P closed if it is closed under the P's power operation. Well, for example, if I have a Russian map and I take D to be the associated foliation, then such D is P closed. But if we start with something which is P closed, usually it's not possible to get like a unique vibration like that. That's simply because when you solve differential equations in characteristic P, you get too many constant functions. Namely, any P's power over function will look like constant in differential geometry in characteristic P, because when you take a derivative, you get a 0. Okay, then there's a fact. So if you put a P-closed condition on foliations in characteristic P, then you will relate that to purely inseparable morphisms. So the way to do it is, okay, so we start with dx, which is P-closed. Then we set we did set some shift to be all functions on x such that it's killed by this p. Then we have the inclusion to the this to the p power. Because any function you raise to the p power, well, it's not quite. Should be f to the p. Well, that's because any function which is a p power, then you apply the differential operators to that, so you will get a 0. So, and we take x prime to be spec of this sheaf of algebra. Okay. So then this inclusion will give you, so what we get is x prime these are all defined over k. Because you know that, I mean, all the functions inside the field are constant functions. So k is included over there. And so everything is defined over k. So what now we define this x prime. We usually also call this x prime to be x divided by the foliation. So that's, you also call x, that's like an x quotient by the foliation. Let's call this f, g, and so both f and g are purely inseparable. And also, G composed F equals the relative Frobenius of X. There is a conjecture on the algebraic integrability of foliations by relating foliations in characteristic 0 and then in that in characteristic p. Well, I think that conjecture is well, quite nice, so I would like to state it here. Oh, here I forgot to say that before I get this, then from there you can get the foliation back. We also have this d equals x over x prime. Well, before going to the arithmetic theory of foliations, I would say a bit about why we only define like integrability for characteristic 0, not the characteristic p. It's basically the following. So, for a p closed foliation, we can think of that as basically as the first order some first order vibration, which means the following: if we have some vibration on x, then of course on x we can define a d, and this is the relative tangent sheaf. Then you can do the quotient as there. So you get x1. This is x over b. Now, because the directions here are vertical, so all functions coming from b are killed by this foliation. So that means function of b is contained, can be viewed as like functions on x1. So you have a factorization like this. Now again, so on x1 you have a fibration. So you can do the same check. You get x2, which is x1 modulo some d1, which lives on x1, and so on. So, okay, now di is just a modular. So in characteristic P, so a fibration, to get a fibration, you need something more than just a foliation. You need a foliation, and then again a foliation on the quotient, another foliation on the second quotient, and so on. So you need a sequence of foliations to really determine a fibration. Of course, this sequence has to satisfy some compatibility conditions. Otherwise, it's not coming from a fibration. So a fibration contains much more information than simply a P-closed foliation. Well, it's you can. Well, it's. You can think of it like if x equals, spec. You can spec of the k x y, and the d is given by one direction. Then you get x prime will basically spec k x to the p y. So that's the relation between them. It's a very nice, purely inseparable finite morphism between them. Well, you can think of this as a partial Frobenius, because the total Frobenius will also raise y to the pth power. But the foliation will give only to on x. What arithmetic theory? Well, actually, it's not a theory; it's just a conjecture. So now we start with x over the complex numbers, and d, which is defined over also complex number. So this is a foliation. Okay, and what you do is now then we take some R inside C, which is finitely generated over Z, such that everything can be defined over this R. So you can extend this x to some x over spec R. And here d is to some d tilde inside okay, so when you do this, then you can, one nice thing is you can take maximal I.
Is that a ring or a field?
It's a ring.
Finite generated over the I.
Take some finite generated over Z.
Sorry, I'm a little bit behind. Sorry.
Now, then you can expand everything, from basically the C point to a open, theoretical open set. Let's say you get a model defined over R, and you want this D also extended to R. Then you can do mod P reduction, because inside R you have a lot of maximal ideas. After doing the reduction, we'll get some foliation in characteristic P. So, for any maximal ideal P inside R, we can do get this XP. And we also have this D P, which is this D tilde mod the maximum ideal P here. This is inside. Let me shift XP over the field, radial field and P. Okay, now then you consider this condition. The D mod P is P closed, where P is the characteristic of the radial field for almost all. For almost all maximal ideals. When it turns out that this condition, I mean this is due to Cots, I guess. The choose of star is independent of the choice. Namely, if you choose one such R and the star holds, then it will hold for all choices of R. And the conjecture I would say, okay, this first is a general version of Grothendieck. Cots, P curvature conjecture, and then this version, the general version I'm going to state, first appeared in a preprint of Ekdal and Schäfer-Brun. And Taylor. Well, it says the following. This D is algebraically integrable if and only if this condition star holds. Well, one direction is easy. If D is algebraically integrable, that means D comes from some rational map from X to some B. Then you can also, well, choose your R such that X mapped to B is defined over R. Then when you mod P, you will see that each time the foliation mod P is also comes from the fibration mod P. So it's P closed. So then that's one direction. But the other direction is extremely difficult. But at least when you have some foliation and you want to test whether it comes from some fibration or not, you can do this. You can check this star condition, and maybe that will give you some extra information about the foliation, and eventually you can say something in your specific case. Just remark that the Grothendieck-Cots conjecture is, it's a special version of this. Namely, you take your X to be a vector bundle over some base, and the distribution, the foliation D will be given by some connection on that bundle. And this more general version first appeared inside their preprint. Right. Okay. Now, this is a more introduction to foliations. I almost used up my time. Now I will tell you how to construct such kind of foliations using rational curves. And when those are like if the foliation is constructed from some specific geometry, then sometimes you can hope to maybe get some vibration from that. Okay, don't have time for examples. Let me just go directly to foliations from rational curves. Well, a rational curve I would mean a non-constant map from P1 to right x, so non-constant. Okay. Then you have the notion of rationally chain connected. So if a general pair of points can be connected by a chain of rational curves, then you also have the notion of rationally connected. So a general pair of points can be connected by one rational curve. So that's the, and then you have the notion of separably. Okay, let me still define the free rational curve. Means while P1 is inside a smooth locus, and X splits as a direct sum of line bundles with all non-negative degree. And if you vary free, rational curve means basically the same, but here you require this AIs to be all positive. Okay. Now, then we have a separably rationally connected. That means X contains a very free rational curve. Well, in particular, like the formations of this very free rational curve will connect the general pair of points. So in particular, they would be rationally connected. And I define this notion of F also is freely rationally connected. Well, this means a general pair of points can be connected by a free rational curve. So this is some notion kind of sitting between SRC and RC. Now, we know that in characteristic 0, and X is a smooth projective, then rationally chain connected is equivalent to rationally connected, equivalent to freely rationally connected, and separably rationally connected. So they are all equivalent. Now in characteristic P, now we know that in general, of course, this is the strongest, and here, well, those implications are always true with in any characteristic. But the other direction, we know that well, this we don't know. And okay. For here, we know that this does not imply FRC. There exists rationally connected varieties which are not freely rationally connected. And there exists freely rationally connected, but not separably rationally connected. So some kind of stringy phenomena happens in characteristic P. So then, using the notion of a foliation, we want to study the relation between those two. The main result I'm going to state basically says that they are the same up to some purely inseparable morphism. Okay, let's see how to construct that. Okay, now if phi from P1 to X is free, then we define the positive part of phi observed Px to be direct sum of the copies where AI are positive. So this is a set of phi observed Px. Now we define the positive rank of your X. If X contains a free rational curve, then you can define this as the max of the possible rank of the positive part when this phi is free. You take all possible free rational curves, and you pull back the tangent bundle, you take the positive part of the pullback, then you take the rank, and you take the maximum of all possible ranks. So that means then with this notion, so S or C, namely all the AIs are positive for some curve is equivalent to saying that the positive rank of X is equal to the dimension of X. Okay, so that's kind of clear. Okay, now so the construction. Okay, we restrict. Actually, the construction of the foliation, can be 0 or P here. So X is over some field K, and we assume that it contains a free rational curve. Okay. Now, then the first step of the construction is we take some general point of X. So say this is a point X. Now I take some curve C1 and a curve. This is curve C2. Okay, both are free. This is all free, and we also require this to be something called maximally free. Namely, we want the rank of the positive part of X restricted to C1 is to be the maximum possible.
Sorry, what are you doing now? You're constructing what?
I'm constructing foliation. Construction of.
So what's the characteristic? Any characteristic?
This can be any characteristic, but it will be only interesting.
The text contains a free rational curve, and then you're constructing a foliation.
Yes, yes. Yeah. Over D. Okay, now, so through some general points, you take two free rational curves, and you require one of them to have the positive rank to be the maximum possible. Then, well, you can say.
You can really rule it. Just the one rational curve for the general point. If you have if I write, you have just one rational curve.
If you only have one, then they're the same.
You have done. Okay.
Yeah.
Okay. I was confused by your picture because with that.
Okay. Yeah. If you only have one, then yeah. Okay. The first says that the positive part of well, you restrict the tangent shift to C1, then take the positive part and look at the point X. This will always contain a positive part of okay, so in other words, we define this d sub x to be the positive part of some of the tangent shift restricted to some C1 with maximal positive rank. Then this is independent of the choice of your curve C1. It's I mean, it only depends on the point X, because if you have two C1s and both are both are maximal, so one contains the other and the other contains the one, so they are the same. That's the first. The second step is, well, you just take all. Well, these are subspaces. So this dx, in particular, d sub x is a subspace of the tangent shift at x. But then you put all them together. It turns out that this, I mean, of course you can you don't define a shift like just using and put the stocks together, but it turns out that this is a subsheaf. Well, then the way you do it is using faithfully flat descent, and actually it's a foliation. The way to check that it's a foliation is using the positivity of d along free rational curves, because if you check the Lie bracket, what you do is you take a d tensor d and map to the tangent bundle modulo by d, which is OX linear. You restrict this Lie bracket operation to a rational curve. You will get some homomorphism from d tensor d to the quotient of tx by d. On the curve, d is positive, and the quotient is kind of trivial, so you do not have non-trivial